Below in this lecture, we'll answer two questions. The first question, we find out the area of this trapezoid ABCD. And in the second question, we find out the area of this quadrilateral ABCD using two different methods. So we start with the first question. In the drawing, we have trapezoid ABCD. This circle is inscribed by trapezoid ABCD. Side DA of trapezoid ABCD equals to 41 units in its length. Side CB equals to also 41 units. Side AB equals to 50 units in its length. And our task is to find out the area of this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is trapezoid ABCD. Side DC is parallel to side AB. So in quadrilateral ABCD, side DC is parallel to side AB, and therefore quadrilateral ABCD is a trapezoid. If we define the length of side DC as A and the length of side AB as B, then the area of this trapezoid ABCD, is equals to the sum of its two parallel bases, that is to say AB plus B times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. I repeat again, the area of this trapezoid ABCD equals to the sum of its two parallel bases. In this case it is A plus B times the height edge over 2. First of all, we define the point of tendency of tangent DC with this circle, this point E. Likewise, we define the point of tendency of tangent DA with this circle, this point F. We define the point of tendency of tangent CB with this circle, this point H. And finally, we define the point of tendency of tangent AB with this circle, this point H, this point J. Here we can implement rule 2. We take quickly on rule 2. According to rule 2, the lengths of two tangents from a common start point to a circle are equal. In the drawing, we have a circle. This is the common start point P. From this common start point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, we focus on this common external point D. We focus on this common external point D. From this common external point D, we have two tangents to this circle, tangent DE and tangent DF. And according to rule 2, they are equal to each other. That is to say, DE equals to DF. So if we define the length of tangent DE as A, then the length of tangent DF must be also equal to A because they are equal to each other according to rule 2. Likewise, if we focus on this common start point C, from this common start point C, we have two tangents to this circle, tangent CE and tangent CH, and according to rule 2, they are equal to each other. That is to say, CE equals to CH. So if we define the length of tangent CE as B, that is to say, tangent CE equals to B units in its length. Then the length of tangent CS must be equal to B because they are equal to each other according to rule 2. Likewise, we will focus on this common start point A. On this connection point A, we have two tangents to the second, tangent AF and tangent AJ. And according to all two, they are equal to each other. That is to say, AF equals to AJ. So if we define the length from tangent AF as C, then the length from tangent AJ must be equal to C. Because they are equal to each other according to all two. And finally, we focus on this connection point B. On this connection point B, we have two tangents to the second, tangent BJ and tangent BH. And according to all two, they are equal to each other. That is to say, BJ equals to BH. So if we define the length from tangent BJ as D, then the length from tangent BH must be also equal to D because they are equal to each other according to all two. So what is the length of side DA plus the opposite side CB? DA plus the opposite side CB in total is equal to A plus B plus C plus D. And again, I should find out that in trapezoid ABCD, side DA plus the opposite side CB equals to A plus B plus C plus D. What is the length of side DC plus the opposite side AB? DC plus AB in total equals to A plus B plus C plus D. So if we found out that those two expressions are both equal to A plus B plus C plus D, and therefore they are equal to each other. That is to say, DA plus CB equals to DC plus AB. So write it down. If we found out that DA plus CB equals to DC plus AB. DA equals to 41 units in its length, plus CB also equals to 41 units in its length, and it is equals to DC. DC is the missing sign, so we leave this it is, plus AB. AB equals to 50 units in its length. So in total, if we found out that 41 plus 41 equals to DC plus 50. 41 plus 41 is 82. So 82 equals to DC plus 50. Here we subtract 50 from this equation, and we get that the missing side DC is equal to 82 minus 50 is 32. So DC equals to 32 units in its length. This is the missing side DC. Is equals to 32 units in its length. In the next step, we will do a construction. That is to say, from point C, we will draw perpendicular on AB. Again, from point C, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. In the next step, we will do another construction. That is to say, from point D, we will do perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB. This point is point N. We know that ABCD is a trapezoid. Therefore, side in trapezoid ABCD, side DC is parallel to side AB. Those two angles are both defined as one-sided interangles, and they are located between the parallel lines DC and AB. And therefore, the sum of those two one-sided interangles is equal to 180 degrees according to Rule 17. So if we click on Rule 17, according to Rule 17, the sum of one-sided interangles that are located between two parallel lines is equal to 180 degrees. In the drawing, we have line A that is parallel to line B, line C cuts those two parallel lines A and B, those 2 points. Those two angles alpha and beta, they are both defined as one-sided interangles. And because of the fact that line A is parallel to line B, it means that they are located between two parallel lines, and therefore the sum of those two one-sided interangles must be equal to 180 degrees. So alpha plus beta equals to 180 degrees according to this rule, Rule 17. So we can actually implement Rule 17 in our drawing. Why? Because in our drawing, side DC is parallel to side AB, and those two angles, they are defined as one-sided interangles, and they are located between the parallel lines DC and AB. And therefore, according to Rule 17, the sum of those two one-sided interangles must be equal to 180 degrees. So I write it down. This angle equals to 90 degrees, plus this missing angle, that is actually angle DCJ, in total, they must be equal to 180 degrees according to Rule 17. Repeat again. The sum of the two one-sided interangles equals to 180 degrees according to Rule 17. Why? Because they are located between the parallel lines DC and AB, therefore the sum of those two one-sided interangles must be equal to 180 degrees. So 90 degrees plus the missing angle DCJ, in total must be equal to 180 degrees. Here we subtract 90 degrees from the equation, and we get that the missing angle DCJ is equal to 180 degrees minus 90 degrees is 90 degrees. So actually, this is the missing angle DCJ that is equal to 90 degrees in its size. This is a right angle. Those two angles are also defined as one-sided interangles and they are located between the parallel lines DC and AB. And therefore the sum of those two one-sided interangles must be equal to 180 degrees according to rule 17. So this angle is a right angle plus this missing angle that is actually angle CDN. In total, the sum of those two one-sided interangles must be equal to 180 degrees according to rule 17 because they are located between the parallel lines DC and AB. Repeating again. The sum of those two one-sided interangles is 90 degrees plus the missing angle CDN. In total, they must be equal to 180 degrees according to rule 17. So here we subtract 90 degrees from this equation and finally get that the missing angle CDN is equal to 180 degrees minus 90 degrees is 90 degrees. So actually, this is the missing angle CDN, this is equal to 90 degrees in its size. It is a right angle. So if we found out that in quadrangle DCJN, in this quadrangle we have 4 right angles. And therefore quadrangle DCJN is a right angle according to rule 5. So as you know, this is quadrangle DCGN, and it is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCJN, side DC must be equal to the opposite side JN. But DC is 32, therefore the opposite side NJ or JN must be equal also to 32 units in its length. Likewise, according to the sum rule, in the sum of the DCJN, side DC must be equal to the opposite side CJ. So DN equals to CJ. According to the rule, that the opposite sides of a rectangle are equal to each other. In the next step, we will focus on those two right angles. On this right angle CJB and this right angle DNA. Actually, those two right angles can go into each other according to side rule. That is to say, those two sides, they are both equal to 41 degrees, therefore they are equal to each other. In addition, those two sides, they are equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. And finally, those two sides are also equal to each other. So we will prove that those two sides must be equal to each other. So actually I copied these two right angles in an equation. I proved that those two sides are equal to each other. So actually, those are the two right angles that are copied from John Darwin. The hypotenuse DA equals to the hypotenuse CB. So we define the length of DA is y. It's y, then therefore side CB must be also equal to y because they are equal to each other. Actually, the hypotenuse equals to 41, but anyway, I define it as y. Okay, so those two sides are both equal to y, therefore they are equal to each other. Those two sides are equal to each other. According to the rule that the opposite sides of a rectangle are equal to each other. So if we define the length of this side as x, then this side must be also equal to x. And finally, while those two sides are equal to each other, here we implemented the particle theorem on this right triangle DNA. This one again according to the Pythagoras theorem, y squared equals to x squared plus an squared. Again, y squared equals to x squared plus an squared. Here we subtracted x squared from this equation and finally found out that an squared equals to y squared minus x squared. Here we took root out of this equation and finally found out that an equals to the square root of y squared minus x squared. Repeated on the same process of this right triangle CJB. According to the Pythagoras theorem, in this right triangle CJB, y squared equals to x squared plus jb squared. Again, y squared equals to x squared plus jb squared. Here we subtract x squared from the equation and finally found out that jb squared equals to y squared minus x squared. Here we took out of this equation and finally found out that jb equals to the square root of y squared minus x squared. So those two sides, they are both equal to the square root of y squared minus x squared, and therefore they are equal to each other. That is to say, an equals to jb. So in total, we found out that all the three sides of this right triangle DNA corresponding equal to all the three sides of this right triangle CJB, and therefore those two right triangles can go into each other according to side rule. So at the moment we found out that the right triangle DNA can go into the right triangle CJB according to side rule. Because again, we found out that the right triangle DNA can go into the right triangle CJB according to side rule. From the fact that those two right triangles can go into each other, we will derive that side AN of the right triangle DNA is equal to side JB of the right triangle CJB. So it is known NA equals to NA equals to JB. And again, side NA of the right triangle DNA is equal to side JB of the right triangle CJB. So if we define the length of side AN as x, then the length of side JB must be also equal to x because they are equal to each other. From one side, AB equals to 50 units according to what is given to the question. But from the other side, AB in total equals to AN plus NJ plus JB. That is to say, AB equals to AN, that is x, plus NJ, that is 32, plus JB, that is x. And again, from one side, AB equals to 50 units in itself, according to what is given in the question, but from the other side, AB also equals to x plus 32. So from this equation, we derive that 50 equals to 2x plus 32. Here we subtract 32 from the equation, and finally we get that 2x equals to 50 minus 32 is 18, so 2x equals to 18. Here we divide this equation by 2, and finally we get that x equals to 18 over 2 is 9, so x equals to 9 units in itself. A equals to x and x equals to 9. Here JB also equals to x and x equals to 9 units in its name. In the next step, I'll copy the right triangle CJB in a new page and we'll implement the Pythagoras theorem of this right triangle, triangle CJB. Here by PT is the equation for Pythagoras theorem. The hypotenuse CB equals to 41 units in its name, the sine JB equals to 9 units in its name. So actually, this is the right triangle CJB, that according to the original drawing, in this right triangle CJB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. So it is known. CB squared, that is the square of the hypotenuse, equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared, which is 1681, and is equals to CJ squared. CJ is the missing side, so we leave it as it is. So it is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. So in total, we found out that 1681 equals to CJ squared plus 81. Here we subtract 81 from this equation and find again that 1681 minus 81 is 1600 and it is equal to CJ squared. So CJ squared equals to 1800. Here we take out all of this equation and find again that the missing sign CJ is equal to the square root of 1600, that is 40. So CJ equals to 40 units in its name. This is side CJ, this is equal to 40 units in its name. CJ is actually the height of trapezoid ABCD. We know that the height of trapezoid ABCD equals to 40 units in its length. Our task is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? According to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is actually DC plus AB, times the height is CJ over 2. But again, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is actually DC plus AB, times the height CJ over 2. So the area of trapezoid ABCD in total must be equal to DC is 32. This is 32. Plus AB. AB is 50. Times the height CJ. CJ is 40. Divided by 2. So in total, there of this trapezoid ABCD is equal to 32 plus 50 is 82, and 40 over 2 is 20. So in total, there of trapezoid ABCD equals to 82 times 20, that is 1640 square units in its size. And that is the answer to the question. And again, if you found out that the area that we are looking for in this question, that is the area on this trapezoid ABCD is equal to 1640 square units in its size. Okay, so we finish with the first question. In the next step, I'll present to you the second question, and we'll solve the second question by using two methods. The second question, our task is to find out the area of this quadrigonal ABCD. So in the drawing we have quadrigonal ABCD, side AB equals to 10 units in its length, side DC equals to 25 units in its length. This is angle ABC, that is a right angle. This is angle ADC, that is also a right angle. This is angle BCD, that is equal to 45 degrees in its size. Again, our task is to find out the area of this quadrigonal ABCD. So first of all, we will do a construction. That is to say, from point B, we will do perpendicular on DC. Again, from point B, we will do perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC. This point is point N. The next step we will do another construction. That is to say, from this point, point A, we will do perpendicular on BN. Again, from point A, we will do perpendicular on BN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BN. This point is point M. By doing this construction, we will do quadrigonal AM and D. Inside quadrigonal AM and D, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. For 270 degrees plus the size of this fourth missing angle, so that they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrigonal is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrigonal AM and D, we have 4 angles, and therefore according to rule 5, quadrigonal AM and D is rectangle. So as you know, this is quadrigonal AM and D. This is a rectangle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. We will define the length of side AM SA. So in rectangle, AM and D, side AM must be equal to the opposite side DN. Only to the order the opposite sides of rectangle are equal to each other. But AM is A, therefore the opposite side DN must be also equal to A units in its length. What is the length from this missing line segment NC? From the drawing it is very easy to see that NC in total equals to DC minus DN. Again, NC equals to DC minus DN. So write it down. NC equals to DC minus DN. So NC in total equals to DC is 25 minus DN is A. So in total NC equals to 25 minus A units in its length. This is line segment NC, that is equals to 25 minus A units in its length. In the next step we'll focus on this right triangle, triangle B and C. In the right triangle B and C, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. 45 degrees plus 45 degrees is 90 degrees, 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. We will continue to focus on this right triangle B and C. In the right triangle B and C, we have the rule that states that in front of equal angles in a triangle, there are equal sides. So in front those two equal angles, we have those two sides that must be also equal to each other in their lengths. But NC is 25 minus A. Therefore BN must be also equal to 25 minus A units in its length, according to the rule that I mentioned. So side BN equals to 25 minus A units in its length. It is given as a question that the big angle ABC equals to 90 degrees in its size. So the big angle ABC minus this angle that is 45 degrees must be equal to the missing angle ABM. Okay. Angle ABC, that is the right angle, minus this angle that is 45 degrees must be equal to the missing angle ABM, this angle. So 90 degrees minus 45 degrees is 45 degrees. Therefore this missing angle ABM must be equal to 45 degrees in its size. In the small right triangle A and B, this right triangle BM, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this furthest angle must be equal to 45 degrees in its side, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. We continue to focus on this small right triangle ABM, and the small right triangle ABM, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But side AM equals to A units in its length, and therefore side BM must also equal to A units in its length. AM equals to A units in its length. What is the length of this missing line segment MN? From the drawing it is very easy to see that MN equals to Bn minus Bm. Again, Bn minus Bm equals to Mn. So adding on, Mn equals to Bn minus Bm. So Mn in total equals to Bn. Bn is 25 minus A minus Bm. Bm is A. So total Mn equals to 25 minus A. Minus A is 25 minus 2A. So that's Mn equals to 25 minus 2A units in its length. 25 minus 2A. In rectangle AM and D, the opposite sides are equal to each other. That is to say, side MN must be equal to the opposite side AD, but MN is 25 minus 2A, therefore AD must be also equal to 25 minus 2A units in its length. So that's it now. AD is also equal to 25 minus 2A units in its length. In the next step, we will implement the Pythagoras theorem of this for right angle MBA. So copy the right angle MBA in a new page, and we will implement on it the Pythagoras theorem. According to the Pythagoras theorem, in a right angle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. Here by PT is the equation for Pythagoras theorem. So here, this is the right small triangle ABM, the copy from the original drawing. This right triangle ABM, according to the Pythagoras theorem, BA squared, that is the square of the hypotenuse, equals to BM squared plus MA squared. So write it down. So BA squared, that is the square of the hypotenuse, equals to BM squared plus MA squared. BA is 10, therefore BA squared is 10 squared, that is 100, and it is equals to BM squared. BM is A, therefore BM squared is A squared, plus MA squared. MA is also MA is also A, therefore MA squared is A squared. So A squared plus A squared is 2A squared, so in total we found out that 100 equals to 2A squared, or 2A squared equals to 100. This is quadrilateral A, B, and D. Quadrilateral A, B, and D is a trapezoid. Why? Because first of all, we know that in rectangle AM and D, side MN is parallel to the opposite side AD. But BN, the segment BN is a straight line because angle BMN is 180 degrees, and you know that any angle that is equal to 180 degrees in size, it is defined as a straight line. So BN is a straight line, and you know that part of the straight line BN, that is MN, is parallel to AD. And if a part of the straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. So the straight line BN itself must be also parallel to AD. And because of the fact that in quadrilateral A, B, and D, side BN is parallel to the opposite side AD, this is exactly the definition of a trapezoid. Quadrilateral A, B, and D has one pair of parallel sides. Side BN is parallel to side AD, and therefore quadrilateral A, B, and D is a trapezoid. So write it down. She found that quadrilateral A, B, and D is a trapezoid. And again, quadrilateral A, B, and D is a trapezoid because it has one pair of parallel sides. In the next step, we'll find out the area of trapezoid A, B, and D. So what is the area of trapezoid A, B, and D? In the beginning of the lecture, I presented to you the formula of the area of a trapezoid. The area of trapezoid equals to the sum of its two parallel bases. In this case, it is BN plus AD times the height, that is AM over 2. Again, if you want to know that the area of this trapezoid A, B, and D, in total equals to the sum of its two parallel sides, that is the sum of its two parallel bases, that is BN plus AD, times the height AM over 2. BN is 25 minus A, plus AD is 25 minus 2A, times AM is 8, divided by 2. So total, if you want to do the area of this trapezoid A, B, and D equals to 25 minus A plus 25 minus 2A times A over 2. 25 plus 25 is 50. Minus A minus 2A is minus 3A times A over 2. 50 minus A is 50A. Minus 3A times A is minus 3A squared divided by 2. So total, we found out that the area of trapezoid A, B, and D equals to 50A minus 3A squared over 2. And again, the area of trapezoid A, B, and D equals to 50A minus 3A squared over 2. The area of trapezoid A, B, and D equals to 50A minus 3A squared over 2. Our task is to find out the area of this quadrilateral ABCD. So what is the area of quadrilateral ABCD? From the drawing it is very easy to see that the area of quadrilateral ABCD in total equals to the area of trapezoid A, B, and D. Plus the area of the right triangle B and C. Because again, if you found out that the area of this trapezoid ABCD in total equals to the area of trapezoid A, B, and D plus the area of the right triangle B and C. But we already found out that the area of trapezoid A, B, and D equals to 50A minus 3A squared over 2. Plus the area of the right triangle B and C. The area of this right triangle B and C equals to the base and C times the height and B over 2. And again, the area of this right triangle B and C is equals to the base and C times the height and B over 2. So in total, the area of quadrilateral ABCD equals to 50A minus 3A squared over 2 plus NC equals to 25 minus A times NB. NB also equals to 25 minus A, so it is 25 minus A squared. So total we found out that the area of quadrilateral ABCD is equal to 50A minus 3A squared plus 25 minus A squared over 2. So it is 50A minus 3A squared plus 25 minus A squared. Here we'll open the brackets of this expression and we get that 25 minus A squared equals to 25 squared, that is 625, plus A squared minus 2 times 25 times 8, that is minus 50A divided by 2. 50A minus 50A is 0. So those expressions will get cancelled. And we're left with minus 3A squared plus A squared is minus 2A squared plus 625 divided by 2. So in total we found out that the area of quadrilateral ABCD in total it is equal to 625 minus 2A squared over 2. But we already found out that 2A squared equals 200. We already found out that 2A squared equals 200. Therefore, we substitute 2A squared in this equation by 100 and you get that the area of quadrilateral ABCD in total equals to 625 minus 2A squared. 2A squared is 100 divided by 2. 625 minus 100 is 525 over 2. 525 over 2 is 262.5 square units in its size. So in total we should know that the area that we are looking for this question, that is the area of this quadrilateral ABCD, is equal to 262.5 square units in its size. So finish the first method. In the next step, I will present to you how to find out the area of this quadrilateral ABCD according to the second method. In the second method, we will do a construction. That is to say, we will extend side DA and side CB of this quadrilateral ABCD by a straight line until they touch each other. So actually, this is their touching point. We'll define this their touching point as M. By doing this construction, we can deduce the right big triangle MDC. In the right big triangle MDC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this first angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We'll continue to focus on the right big triangle MDC. In the right big triangle MDC, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But side DC is 25, therefore side MD must be also equal to 25 units in its length. So MD equals to 25 units in its length. MC is the hypotenuse of the right big triangle MDC. So MC is an hypotenuse, it is absolutely a straight line. So if we focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the left side of the straight line MC at point B? We have this angle, that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right triangle MBA, the right small triangle MBA, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this first angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. We continue to focus on the small right triangle MBA. The small right triangle MBA, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But side AB is 10, therefore side AB must be also equal to 10 units in its length. MB equals to 10. What is the area of quadrilateral ABCD? From the drawing, it is very easy to see that the area of this quadrilateral ABCD equals to the area of the big right triangle MDC minus the area of the small right triangle MBA. And again, the area of this quadrilateral ABCD, that is the area that we are looking for in this question, is equal to the area of the big right triangle MDC minus the area of the small right triangle MBA. The area of the big right triangle MDC equals to the base DC times the height DM over 2. Okay, again, the area of this big right triangle MDC in total is equals to the base DC times the height DM over 2. minus the area of this small right triangle, MBM. Minus the area of this small right triangle, MBA. The area of this small right triangle, MBA, equals to the base AB times the height MB over 2. And again, this small right triangle, MBA, equals to the base AB times the height MB over 2. DC is 25. DM is also 25, so DC times DM is 25 times 25 over 2. Minus AB, AB is 10 times MB, MB is also 10. So total if you found out the area of this quadrilateral ABCD equals to 25 times 25 minus 10 times 10 over 2. 25 times 25 is 625 minus 10 times 10 is 100 over 2. 65 minus 100 is 525 divided by 2. 525 over 2 is 262.5 square units in size. So if you found out that the area of this quadrilateral ABCD in both methods is equal to 262.5 square units in its size. So we finish with the second question, with the second method of the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. Our task in the first question is to find out the area of this trapezoid ABCD. So, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. But again, a trapezoid is a quadrilateral with one pair of parallel sides. This is trapezoid ABCD. In trapezoid ABCD, side DC is parallel to the opposite side AB. So if we define the length of side DC as A and the length of side AB as B, then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases. The two parallel sides are defined as bases. So the area of trapezoid ABCD equals to the sum of its two parallel bases, that is to say AB, A plus B, times the height H over 2. The height H must create 90 degrees, the two parallel bases. Okay, repeat again, the area of trapezoid, any trapezoid equals to the sum of its two parallel bases times the height over 2. In the next step, we define the point of tendency of tangent DA with this circle, this point F. We define the point of tendency of tangent DC with this circle C. We define the point of tendency of tangent CB with this circle, this point H. And finally, we define the point of tendency of tangent AB with this circle, this point J. In the next step, we implemented rule 2 in our drawing. So, at respect to rule 2, according to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle. This is the common standpoint, point P. From this common standpoint, point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because if we focus on this common standpoint, point D, from this common standpoint, point D, we have two tangents to the circle, tangent DA, tangent DE, tangent DF. And according to rule 2, they are equal to each other. That is to say DE equals to DF. So if you define the length of tangent DE as A, then the length of tangent DF must be also equal to A because they are equal to each other according to rule 2. Likewise, if you focus on this connection point C, on this connection point C, we have two tangents to this equation, tangent CE and tangent CH. And according to rule 2, they are equal to each other. That is to say CE equals to CH. So if you define the length of tangent CE as B, then the length of tangent CH must be also equal to B because they are equal to each other according to rule 2. Likewise, we focus on this connection point A. From this connection point A, we have two tangents to this equation, tangent AF and tangent AJ. And according to rule 2, they are equal to each other. That is to say AF equals to AJ. So if we find the length of tangent AF is C, then the length of tangent AJ must be also equal to C because they are equal to each other according to rule 2. And finally, if we focus on this connection point B, from this connection point B, we have two tangents to this equation, tangent BJ and tangent BH. And according to rule 2, they are equal to each other. That is to say BH equals to BJ. So if we define the length of tangent BH as D, then the length of tangent BJ must be also equal to D because they are equal to each other according to rule 2. So what is the length of side CB plus side DA plus the opposite side DA? DA plus CB in total equals to A plus B plus C plus D. And again, DA plus CB in total equals to A plus B plus C plus D. Likewise, what is the value of side DC plus the opposite side AB? DC plus AB in total equals to A plus B plus C plus D. So if you found out that DC plus AB also equals to A plus B plus C plus D, and because of the fact that those two expressions are both equal to A plus B plus C plus D, they must be equal to each other. That is to say DA plus CB equals to DC plus AB. DA is 41, CB is also 41, DC is the missing side, so leave it as it is, AB is 50. 41 plus 41 is 82, equals to DC plus 50. If subtract 50 from the equation, if I found out the missing side DC equals to 82 minus 50 is 32. So this is the missing side DC, this equals to 32 units in its length. In the next step, we did a construction, that is to say, from point D, we do perpendicular on AB. We define that, so this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and AB, this point is point N. In the next step, we did another construction, that is to say, from point C, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point J. So here we know that trapezoid ABCD, in trapezoid ABCD has one pair of parallel sides. The two the pair of parallel sides is DC is parallel to AB. So DC is parallel to AB in trapezoid ABCD. Those two angles are defined as one-sided interangles and they are located between the parallel lines DC and AB, and therefore the sum of those two angles must be equal to 180 degrees according to rule 17. So this angle equals to 90 degrees plus this missing angle, in total they must be equal to 180 degrees according to rule 17. The missing angle is angle CDN. So again, if you found out that this angle equals to 90 degrees, so 90 degrees plus the missing angle CDN, in total they must be equal to 180 degrees according to rule 17. Here we subtracted 90 degrees from this equation, if I found out that the missing angle CDN equals to 90 degrees in its size. This is the missing angle CDN, this equals to 90 degrees in its size. Likewise, those two angles are defined as one-sided interangles and are located between the parallel lines DC and AB. And therefore, according to rule 17, the sum of those two one-sided interrogants must be equal to 180 degrees. This angle is right angle plus this missing angle, this is actually the angle DCJ, so that must be equal to 180 degrees according to rule 17. Repeat again. 90 degrees plus the missing angle DCJ in total must be equal to 180 degrees according to rule 17. Here we subtract 90 degrees from this equation and we found out that the missing angle DCJ equals to 90 degrees in its size. This is the missing angle DCJ, this is equals to 90 degrees in its size. So in quadrilateral DCJN we have 4 right angles, and therefore quadrilateral DCJN is a right angle. But we also know that the opposite sides of right angle are equal to each other. So in right angle DCJN, side DC must be equal to the opposite side JN. But DC is 32, therefore the opposite side NG or JN must be also equal to 32 units in its length. Likewise, according to the same rule, in the same right angle DCJN, side DN must be equal to the opposite side CJ. Those two sides are equal to each other according to the rule that the opposite sides of a rectangle are equal to each other. So in those two rectangles, those two sides are equal to each other. Those two sides are also equal to each other, each of them equals to 41 degrees. In the next step, we prove that those two sides are also equal to each other. So I copy those two rectangles in a new page and we prove that those two sides are also equal to each other. So actually, those are the two rectangles that are copied from the original domain. We define those two sides that are equal to each other as y, and those two sides that are also equal to each other as x. So in this rectangle DNA, according to the Pythagoras theorem, y squared equals to x squared plus an squared. Again, y squared equals to x squared plus an squared. Here we subtract the x squared from the equation and find out that an squared equals to y squared minus x squared. Here we took a root out of this equation and find out that the length of the missing side an equals to the square root of y squared minus x squared. We repeat on the same process in this right angle CJB. The right angle CJB, according to the Pythagoras theorem, y squared equals to x squared plus JB squared. Again, y squared equals to x squared plus JB squared. Here we subtract the x squared from the equation and find out that JB squared equals to y squared minus x squared. Here we take a root out of this equation and find out that JB, the missing side JB, equals to the square root of y squared minus x squared. So those two sides are both equal to the square root of y squared minus x squared, and therefore they are equal to each other. That is to say, an equals to JB. So we can prove that all the three sides of this right angle DNA correspond equal to the three sides of this right angle CJB, and therefore those two right angles can join to each other according to side rule. But again, we can find out that the right angle DNA can join, this is the side of can join, to the right angle CJB according to side rule. And from the fact that those two right angles can join to each other, we derive that side AN equals to side JB according to the rule that corresponding sides that can join triangles are equal to each other. Those two right angles can join to each other, therefore the two corresponding sides, that is to say AN and JB, must be also equal to each other. Okay, so here we derive that AN equals to JB. So if we define the length of AN as x, then JB must be also equal to x because they are equal to each other. AB from one side equals to 50 according to what is given in the question, but from the other side is equals to x plus 32. And again, if you find out that from one side AB equals to 50, but from the other side it is equals to x plus 32. So 50 equals to 2x plus 32. We have subtracted 32 from this equation and found out that 2x equals to 32 minus 50 minus 32 is 18. So 2x equals to 18. Here we divided this equation by 2 and found out that x equals to 9 units in its length. So here x equals to 9 units in its length. In the next step, I copied the right angle CJB in a new page and implemented the Pythagoras theorem of this right angle CJB. So actually, this is right angle CJB, this is coming from the horizontal, and this right angle CJB, CB squared, that is the square they are produced, equals to CJ squared plus JB squared. CB is 41, therefore CB squared is 41 squared, that is 681, plus CJ squared. CJ is the missing side, so it is. So it is CJ squared plus JB squared. JB is 9, therefore JB squared is 9 squared, that is 81. So in total we should find out that 681 equals to CJ squared plus 81. We subtract 81 from this equation, and we found out that CJ squared equals to 681 minus 81 is 600. So 600 equals to CJ squared, or CJ squared equals to 600. Here we took out of the equation, and we found out that the missing side CJ equals to the square root of 1600, that is 40. So CJ equals to 40 units in itself. This is side CJ, that equals to 40 units in itself. Actually CJ is the height of trapezoid ABCD. Our task is to find out the area of this trapezoid ABCD. According to the formula that I presented to you in the beginning of the lecture, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is to say DC plus AB times the height CJ over 2. If you get the area of trapezoid ABCD, total equals to the sum of its two parallel bases, that is actually DC plus AB, times the height CJ over 2. DC is 32, AB is 50, and CJ is 40, divided by 2. 32 plus 50 is 82, and 40 over 2 is 20. So we found out that the area of this trapezoid ABCD equals to 82 times 20, 82 times 20, that is 640 square meters in its size. Again, the area of this trapezoid ABCD equals to 1640 square units in its size. So we finished with the first question. In the next step, I presented you the second question, and we solved the second question by using two different methods. In the second question, our task is to find out the area of this quadrangle ABCD. So at the moment we have quadrangle ABCD. Side AB equals to 10 units in itself, side DC equals to 25 units in itself. This is angle ABC, this is right angle. This is angle ADC, this is also right angle. This is angle BCD, this is equal to 45 degrees in its size. Again, our task is to find out the area of this quadrangle ABCD. So first of all, we did a construction. That is to say, from point B, we do perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC. This point is point N. We did another construction, that is to say, from point A, we do perpendicular on BN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BN. This point is point N. By doing this construction, we have the quadrangle AM and D. Inside quadrangle AM and D, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this 4 pieces again, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in its size. So in quadrangle AM and D we have 4 degrees, and therefore quadrangle AM and D is a rectangle. We define the left of side AM as A. We know that the opposite sides of rectangle are equal to each other. So in rectangle AM and D, side AM must be equal to the opposite side DN. But AM is 8, therefore the opposite side DN must be also equal to A units in its length. In the next step, we focus on this right angle B and C. The right angle B and C, this angle equals to 45 degrees, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. 45 degrees plus 45 degrees is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. So in the right triangle B and C, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But NC equals to DC, that is 25, minus the end, that is 8. So in total, NC equals to 25 minus 8. So in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But NC is 25 minus 8, therefore BN must be also equal to 25 minus 8 units in its length. This is angle ABC, that is equal to 90 degrees in its size. So 90 degrees minus 45 degrees is the size of this angle ABM. So the size of angle ABM equals 90 degrees minus 45 degrees, that is 45 degrees. So angle ABM equals to 45 degrees in its size. This angle equals to 90 degrees, and therefore this first angle must be equal to 45 degrees in its size. According to the rule that the sum of the angles in the entire angle is equal to 180 degrees. So in the right triangle ABM, in the small right triangle ABM, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. But AM equals to A, therefore BM must be also equal to A. What is the length of this missing line 70 MN? MN equals to BN minus BM. Again, MN equals to BN minus BM. So MN equals in total to BN, that is 25 minus A, minus BM, that is A. So in total, MN equals to 25 minus A minus A, that is 25 minus 2A. MN equals to 25 minus 2A. So in the rectangle AM and D, the opposite sides are equal to each other. That is to say, side AMN must be equal to the opposite side AD, but AMN is 25 minus 2A, therefore AD must be also equal to 25 minus 2A units in its length. In the next step, we implemented the Pythagoras theorem on this small right triangle ABM. We have covered the small right triangle ABM in the equation. We implemented the Pythagoras theorem. This is the right triangle ABM, this is the copied from the original domain. This right triangle ABM, according to the Pythagoras theorem, BA squared, that is the square of the hypotenuse, equals to BM squared plus AM squared. BA is 10, therefore BA squared is 10 squared, that is 100. And this is equals to BM squared. BM is 8, therefore BM squared is 8 squared plus AM squared. AM is also 8, therefore AM squared is 8 squared. So in total, M squared equals to 8 squared plus 8 squared, that is 2A squared. In total, we should find out that 100 equals to 2A squared. This is quadrilateral A, B, and D. Quadrilateral A, B, and D is a trapezoid. Why? Because we prove that side BN is parallel to side AD. Why side BN is parallel to side AD? First of all, side MN is parallel to side AD according to the rule that the opposite sides of a rectangle are parallel to each other. But BN is a straight line. Why BN is a straight line? Because this is an angle BMN that is equal to 180 degrees in its size, and we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, BN is a straight line. But BN is part of the line 70MN that is parallel to AN. So if a part of a straight line is parallel to another straight line, then the straight line itself, BN, must be also parallel to the other straight line. So BN is parallel to AD. So in quadrilateral A, B, and D, side BN is parallel to the opposite side AD, and therefore quadrilateral A, B, and D is a trapezoid because it has one pair of parallel sides. So what is the area of trapezoid A, B, and D? Quadrilateral A, B, and D is a trapezoid because it has one pair of parallel sides. What is the area of this trapezoid A, B, and D? The area of trapezoid A, B, and D must be equal to the sum of its two parallel sides, that is to say BN plus AD times the height AM over 2. So again, the area of trapezoid ABC in total equals to the sum of its two parallel sides, that is to say BN plus AD times the height AM over 2. BN is 25 minus A, plus AD, that is 25 minus 2A, times AM, that is A over 2. 25 plus 25 is 50, minus A minus 2A is minus 3A, times A over 2. So in total, we should find out that we open the bracket here, and found out that 50 times A is 50A, and minus 3A times A is minus 3A squared over 2. So in total, we should find out that the area of this trapezoid A, B, and D is equal to 50 A minus 3A squared over 2. And again, if you find out that there are this trapezoid A, B, and D, in total it is equal to 58 minus 3A squared over 2. Our test is to find out the area of this quadrangle A, B, C, D. What is the area of quadrangle A, B, C, D? It is very easy to see from the drawing that the area of this quadrangle A, B, C, D equals to the area of trapezoid A, B, and D plus the area of this right triangle B and C. Repeat again, the area of this trapezoid A, B, C, D in total is equals to the area of trapezoid A, B, and D plus the area of the right triangle B and C. But we already found out that the area of trapezoid A, B, and D equals to 58 minus 3A squared over 2 plus the area of the right triangle B and C. The area of the right triangle B and C equals to the base and C times the height and B over 2. And again, the area of the right triangle B and C equals to the base and C times the height and B over 2. So in total, the area of quadrangle ABCD equals to 58 minus 3A squared over 2. And C is 25. And C is 25 minus A. And we have here NC is 25 minus A times BN. BN is also 25 minus A, so in total it is 25 minus A squared divided by 2. So total the area of quadrangle ABCD equals to 58 minus 3A squared plus 25 minus A squared over 2. So it is 58 minus 3A squared. We open the brackets here and actually found out that 25 minus A squared in total equals to 25 squared, that is 625 plus A squared plus 2 times 25 times 8, that is minus 58. 58 minus 58 is 0, so those two expressions we get cancelled. We have minus 3A squared plus A squared is minus 2A squared plus 625 divided by 2. So in total, if you found out that the area of this quadrangle ABCD equals to 625 minus 2A squared over 2. But we already found out that 2A squared equals 200. So we can substitute 2A squared here by 100. We did it when we found out that 625 minus 2A squared is minus 100 over 2. So in total, the area of quadrangle ABCD equals to 625 minus 100 over 2. 625 minus 100 is 525 over 2. 525 over 2 equals to 262.5 square meters in size. So if you found out that according to the first method, the area of this quadrangle ABCD equals to 262.5 square meters in size. So we finish the first method. In the next step I presented to you how to find out the area of this quadrangle ABCD according to the second method. In the second method we did the construction, that is to say, we extended side DA and side CB of this quadrangle ABCD by a straight line until they touch each other. We define the attaching point, this point as point M. By doing this construction, we made here the right triangle MDC. The right triangle MDC, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this vertex angle must be equal to 45 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. The hypotenuse MC on the right triangle DMC is an hypotenuse. This is absolutely a straight line. So if you focus on the left side of the straight line MC at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angle we have at the left side of the straight line MC at point B, we have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the small right triangle MBA, this angle equals to 45 degrees, this angle equals to 90 degrees, this angle equals to 45 degrees, and therefore this angle must be equal to 45 degrees in size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle, the small right triangle ABM, in front of those two equal angles, we have those two sides that must be equal to each other. What we do, in front of equal angles in the triangle, there are equal sides. So in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But AB is 10, therefore BM must be also equal to 10 units in its length. Likewise, in the big right triangle MDC, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. But DC is 25, therefore MD must be also equal to 25 units in its length. So what is the area of this quadrangle ABCD? From the comment it's very easy to see that the area of quadrangle ABCD equals to the area of the big right triangle MDC plus the area of the small right triangle MBM. Again, the area of this quadrangle ABCD total must be equal to the area of the big right triangle MDC minus the area of the small right triangle MBA. The area of the big right triangle MDC it is equals to the base TC times the IDM over 2. Okay, the area of the big right triangle MDC equals to the base TC times the IDM over 2. Minus the area of this right triangle MBA. The area of this right triangle MBA equals to the base AB times the IBM over 2. Okay, the area of the small right triangle MBA equals to the base AB times the IB over 2. DC is 25, DM is also 25, minus AB is 10, minus MB is also 10 divided by 2. 25 times 25 is 625, minus 10 times 10 is minus 100 divided by 2. 625 minus 100 is 525 divided by 2. 525 over 2 is 262.5 square units in its size. So in both methods, we have found out that the area of this quadrangle ABCD is equal to 262.5 square units in its size. Okay, thank you very much.